right, let's talk disubstituted cycloalkanes, specifically with stereogenic centers, right? So we got to figure this out. How do we draw? How do we draw a pentagon? You know what I mean? That one will have to do for now. Let's say we got this disubstituted cyclopentane, dibromocyclopentane. We can do two wedges, right? Or maybe we could do. Ooh, I need to do that. Get that nice pentagon going. We could do two dashes, right? These are both cis compounds. Turns out if you flip it over, it's the same compound. Okay, so we can see that because they are, in fact, cis. Now let's draw another one. Got to have that pointed down so it looks pretty. I'm about to copy and paste this so it looks consistent. We've got the bromine wedge in the dash. Now let's draw this mirror. My iPad hates me. Let's draw the wedge, the dash and the wedge. Now we've drawn mirror images of these two cyclopentanes, right? Now let's rotate this particular compound, right? So that means that the bromine on the right is going to be on the left, but it's going to be a dash. If we rotate it, it's not identical to the other compound on the left, and it's not superimposable, right? And so it's not identical. It's a non-superimposable mirror image. So what is that, right? Let's think about that. It's an enantiomer, right? So let's try and figure out some meso compounds. Let's get some practice in so we could be like, Julia Stiles and Sean Patrick Thomas and Save the Last Dance. Great lineup. I mean, they had Kerry Washington in there too. Awesome. So let's check out these cyclohexane rings. Cyclopentane rings. We got disubstituted compounds on each of them, right? So we want to figure out which ones are meso. Make sure you pause the video so you can try this on your own and then double check back to see if you got it right with me. Okay, so let's check it out. All right, so this is a trans compound. This is cis, and so is the bottom. They are cis substituents, right? Now slice it straight through those substituents, and then we'll see what we have. No symmetry here, so this compound is not meso. If we slice this one, the middle one, it is. That does have symmetry, and you get mirror images right there. So that one's meso. If you slice through this cyclopentane ring, the chlorine and the OH are clearly different substituents, so those are not ever going to be mirror images of one another, and it's not meso. So remember, that's all you really need to do is look for the symmetry. If you slice it and dice it and you can't get the mirror images, then it's not meso. Okay, so let's try and draw all stereoisomers that are possible for this 1,2-dimethyl cyclohexane. And then for this, let's see, this one right here, we've got an OH here and a methyl here. So this, and then this cyclobutane, this disubstituted cyclobutane. All right, so make sure that you are pausing the video and trying on your own. And then I'm going to jump through this real quick. We're pointing out stereogenic centers, and those chlorines are not stereogenic centers, or the cyclobutane compound doesn't have any stereogenic centers because that chlorine is bound to a carbon. And if you go to the left and down, or just kind of like the left and right, depending on how you look at the molecule, it's bound. It's just the same trail, the same path, and you're not having any difference in terms of like substituents, and so there's technically no stereogenic center on that. Okay, looking at the top one, redraw each of these compounds with the wedges and the dashes, and basically just switch out the stereogenic center for wedges and dashes and try all your combinations. Also remember that your equation is 2 to the n, where n is a number of stereogenic centers, and so that's, in this case, 4 stereogenic centers. Now, if we were to draw another one, 4 stereoisomers, if we draw another one with the dashes, that is actually the same compound because it's a meso compound and it has symmetry, and therefore we don't have 4 total stereoisomers. We only have 3 on that. Okay. Now, Let's draw again. We give it a wedge and a wedge, right? And then draw another compound where we switch one of those wedges for a dash, okay? Or you can switch both of them if you want first. Depends on how your brain works, right? So let's go ahead and switch both of them to a wedge. And then let's make some more room here. Draw another cyclopentane. And then we want to make sure that we have one of those as a wedge and one of them as a dash. And then we'll go ahead and approach it a little differently this time. Let's go ahead and draw the mirror image of that one. Okay, and so if you were to rotate this molecule, you would see that that OH would no longer be a wedge, it would be a dash, right? And so it's not identical to the compound on the left. So technically we could identify those as enantiomers, right? But it's always good to check your work, and the way to check your work is to go ahead and look at the configurations, right? So let's go ahead. I'm going to draw it over here on the upper right. We'll draw the mirror image of the upper left compound and make sure, see what we got going. Okay, so these are mirror images of one another. Are they identical, or are they, like, what's the relationship between them, right? And so we can obviously see their mirror images, but let's focus on the stereogenic center on our left. We have our 1, 2, 3 priority. That's an R configuration because it rotates to the right. Okay, now let's take a look at the other OH stereogenic center. That's got a 1, 2, 3. That is swapped. It's going counterclockwise, so that's an S configuration. So let's go ahead and erase these for clarity. Now let's get blue and check out the methyl stereogenic center. Okay, so our priority is actually the substituent with that's closest to the OH. And we got 1, 2, 3. That's rotating. The one on the left is rotating counterclockwise. The one on the right is rotating clockwise. So that's R on, and then the one on the left is an S. So what we have, if we want to compare these, what we want to do is make sure that we assign, like, basically compare blues to blues and reds to reds, okay? Because those are the ones with the same substituents on them. So what we have is an RS compared to an SR. Okay, so notice each stereogenic center has been swapped, so the relationship would technically be enantiomers. Yes, you got it. All right, so let's take a look at these lower compounds. We got 1, 2, 3 prioritization. It's a clockwise rotation. That's an R configuration. 1, 2, 3. That gives this an S configuration on the right hand side. Okay, so let's erase those for clarity again. And let's do pretty in blue for the methyl substituents. 1, 2, 3. It's the same prioritization. The wedges don't have any change or effect on that. We can't rotate to the left anymore because remember we have our hydrogen, the lowest priority, projected outward at us now. So I like to use my hand. My thumb is the lowest priority, which is hydrogen in this case. And if I were to close my hand going from 1 to 2 to 3, that would require that I use my right hand. Unless you're like severely double jointed or have a broken hand, I don't know. But the other compound on the right, that stereogenic center, requires me to use my left hand, which makes it an S configuration. Okay, so if I'm using my right hand, it's an R configuration. If I'm using my left hand, it's an S configuration. All right, so what does that mean in the end? We have an RR compared to an SS. Okay, RR, SS. So those also are enantiomers, but their relationship with the above compounds is that they are diastereomers to those. Okay. All right, let's check this bad boy out. We can throw them both wedges, and then we could technically give them both dashes, but those would be the same compound. So let's swap out one of them, and that gives us the trans configuration. Now you might feel inclined, sorry, let me draw it right here. Let's draw the mirror image, right? Right? Excuse me. Now, if I rotate that particular mirror image compound to the right just a little bit, you can see that it's actually the same as the other trans compound that we've drawn. And so these are the only two stereoisomers that we can draw for this particular compound. Because remember, if we draw a cis with dashes, then it's the same compound. We just have to flip it over. Okay, so let's finish it up with some isomers summary. And so we basically want to remember that isomers are basically just different compounds with the same molecular formula. Okay, that's the definition of isomers, but we have different classes of isomers, right? We have constitutional isomers, which are the same molecular formula, of course, because they're isomers, but they are different. They have different bond connectivity, right? So let's say like the oxygen's no longer bound to two carbons, it's bound to an OH or a hydrogen and a carbon, right? So stereoisomers are the other type of isomer that we've seen, which basically are just going over in this chapter, and that's different three-dimensional orientation, but the same bond connectivity. Okay, so it's different than constitutional isomers. So they look the same at a first glance, but we got to look more closely, look at the wedges and the dashes, or just the three-dimensional orientation in general. So we can go to the left and make some enantiomers, and we can go to the right and make some diastereomers. Okay. Now remember, enantiomers are mirror images, but they are non-superimposable. So non-superimposable mirror images of one another. While diastereomers are actually non-superimposable non-mirror images, or non-mirror images and non-superimposable. Okay. Now there's another class of compounds that we also want to remember, and that would be cis and trans isomers. Those are technically stereoisomers, right? And those are specifically what I'm referring to. Like, we do have the cyclohexane, but we've already defined those as like enantiomers or diastereomers, right? So what I'm referring to is the alkenes, right? So we have cis and trans isomers for alkenes, and so we can't forget about those. All right, but that's it for cycloalkanes and isomers. Okay, so let me know if you have any questions.